Log on, tune in, find out. Another good idea from Cambridge.
Motions in image processing. The outline of my talk will go as follows. I'll point out briefly the role of curvatures in visual perception and introduce the multi-scale curvatures. Then I will introduce an algorithm that we termed level line shortening, which is basically an image smoothing algorithm that will serve for denoising as well. And in the end, sorry. Okay. So in the end, I will. Can you hear me? Okay. In the end, I will introduce.
Can we get the full screen?
Or window full screen.
Full screen. Oh.
Full screen.
Sorry. So in the end, I'll talk about a visualization tool that we term image curvature microscope. And this visualization tool runs online on any type of image, and this site I call it. So the first part concerns multi-scale curvature. Sorry. Okay. Now it's this. Okay. I would like to point out that the role of curvatures in visual perception goes back to 1954. And there is a founding paper by Fred and Neil that tries to argue, where he tries to argue the role of these curvatures. And basically his arguments are neurological, and he states that actually our human brain is not capable of registering all of the information that is provided. Namely, if we see an image, we cannot register in our brain all of the information we have in the image. But actually what is retained by our retina are the contours, and even more, the points of the contour at which direction changes abruptly. And these points correspond to curvature extrema. Now, our objective was to try to compute accurately at a subpixel resolution this curvature extrema, and to show that in some sense the computer vision one can do the same as in real life. So here, I'm sorry, the colors, so here curvatures are displayed in yellow when they are 0, and they fade from light red to dark red as they go higher, positive, and in green as they are negative. So sorry, I've tried to change a little bit the colors on the screen, but I couldn't. So this is our objective. Now, one of the major drawbacks in image processing is that most of the images suffer from either aliasing or JPEG artifacts, and one needs to smooth the image or to get rid of these artifacts before computing any features. So our idea was to try to compute these curvatures. Okay, so it's working now. Try to compute these curvatures not on the image itself, but after a pre-processing part directly on level lines. And here is how we do it. Now, before going into details, I'm sure you all know about this, but I want to point out that whenever we talk about digital curvatures or curvatures in a digital image, we can either define a 2D differential operator that is associated to a smooth image and usually at points where the gradient is non-zero. But if the gradient is non-zero, that means that the function, the image itself is locally a graph, so there would be a level line passing by this point. And therefore, we would also have a vectorial curvature. And this vectorial curvature is linked to the scalar by this formula. So this relation suggests already that there are two different ways of computing curvatures, either as a 2D differential operator, like this, or as a 1D differential operator associated to the level line itself. So, however, in both of the cases, as mentioned before, a previous smoothing is necessary to get rid of the artifact. And the smoothing can be either performed for curves or for images. Now, one of the most frequently used smoothing operations is the so-called curve shortening. Now, the curve shortening problem If you're not familiar, states can be shortly presented as follows. Given a curve, which is closed, a Jordan curve, one has to move every point on the curve in the direction of the normal with a speed equal to the curvature. So that will be the speed equal to the curvature, to the vectorial curvature at that point. Now this problem has been studied in the differential geometry setting by Gage and Hamilton for convex curves, and then extended and explored by Grayson for embedded curves in plane, but also on manifolds. As far as the algorithmical part, there are different algorithms, but one of the most robust and that has been served all over these years in image processing is the so-called Maxwell-Maxtorian algorithm, which is an analytical discrete version of an analytical method for computing what the so-called intrinsic heat equation. Now, intrinsic heat equation, because the curvature, whenever we have the natural parametrization, is the second derivative with respect to this parametrization. However, the natural parametrization will change in time. As we evolve, we have to change also the natural parametrization itself. And a variant of the curve shortening problem that is invariant with respect to affine transformations is given by the affine shortening problem, which is basically the evolution of the point with a speed equal to the curvature to 1/3. So this is minus 2/3 because we have k that we have the curvature here that will compensate. Now this problem has been theoretically studied by Sapiro and Tannenbaum and Anken and Sapiro and Tannenbaum, that they showed results similar to Grayson and Gage and Hamilton's. And as far as the algorithmical part is concerned, there are several implementations like finite difference schemes or by using B-spline interpolations, and one of the most robust is given by Moisan, which uses an algorithm called affine erosions. I don't have time to enter into details, but I'll be happy to answer at the end. Okay. On the other hand, as I said before, one can deal with image smoothing. And these two equations are basically the analytical variants of the equations that I've presented before. So here we deal with the mean curvature motion, which will be the level set formulation for the curve shortening problem, and also the affine curvature motion, that will be again the level set formulation for the affine shortening. And among the algorithms, I want to mention the iterative median filter, finite difference schemes, but also the stack filter that will act on level sets. Now, our work is based on these contributions. And the first question before computing the curvature at this subpixel accuracy that we asked ourselves was whether we can give an explicit connection between curve shortening or curve smoothing on one hand and the image smoothing on the other hand. And this is how we were led to introduce the algorithm termed level line shortening. Now the algorithm can be summarized via the following diagram. So we start with an image U0, and this time instead of using the stack filter for the level sets, we use some sort of stack filter for the level lines. So we extract all of the level lines of the image in the discrete case with a subpixel with a certain quantification, and we evolve at the same time independently and simultaneously so all of the level lines. Then we reconstruct back an image which has as level lines these evolutions, and we ask ourselves whether this function reconstructed is actually the analytical evolution for the PDE formulation. And this would give actually an explicit connection between the curve shortening problem and the mean curvature motion, respectively the same results in the affine case. And both in the discrete and in the continuous case, this problem is based on two properties. One is a topological structure, that is, all of the level lines will be embedded in a tree structure, and this is okay. I'll get into details a little bit on the next slide. And the other property is the so-called inclusion principle that is satisfied by the curve shortening problem and also affine shortening. So here is the three-step algorithm represented on images. We start with an image that suffers from pixelization, for which we extract the level lines. Here I have used a quantization step to be able to visualize the level lines. Now, as you can see in this case, level lines we have used a bilinear interpolation, and level lines are pieces of hyperbola concatenated with straight segments. So they suffer of pixelization effects. And in order to get rid of this, if we try to compute directly, the curvature here would be nonsense. We won't have something accurate. So we thought of, what if we smooth out these curves? Now, for the extraction algorithm, I want to point out that there is a fast algorithm called the fast level set transform, introduced by Monaz and Guichard in 2000. But we also recently discovered with Pascal Monaz that we can perform the extraction only by following the intersection with the horizontal lines of the image. So this would be very fast and robust. Okay, once the extraction is performed, we go into the next level of the algorithm, which is the image the level line smoothing. So now this smoothing is in some sense accurate because the level lines are polygonal lines at an arbitrary resolution. So they are polygonal lines with real coordinates. And this allows us to perform a discrete curve shortening such that the inclusion principle is respected. So here we have, as you can observe, the curves that become smoother, so all of the oscillations disappear, and with short time smoothing, we still have the same inclusion respected. This is a topological property that I was talking about. And both for the curve shortening problem and for the affine shortening, this inclusion principle is respected. Now, at the last stage of the algorithm, we take the family of level lines and we reconstruct back the image. And actually, to our surprise, there was no algorithm that could reconstruct an image. Well, this is with sub-pixel accuracy. So there was not an algorithm that could exactly reconstruct the image given a family of level lines for which we only know they are embedded in a tree structure. So we did also this by following intersections with horizontal lines. And it's quite fast. Now, as far as the mathematical consistency is concerned, is given in the setting of viscosity solutions theory. And we showed that by performing this scheme, the function reconstructed by what we term level line shortening is actually a viscosity solution for the mean curvature motion. And the same result will hold for the affine curvature. And I don't have time to get into details, but I will be happy to give an insight at the end. Now, I will pass to the last part, which is the image curvature microscope, which I recall was our objective at the very beginning. So when searching into the literature a little bit, we found that curvatures mostly were computed based on finite difference schemes for the 2D differential operator. But if we have a 2D differential operator, the problem is we take into account the neighborhooding values of the pixels. So for each pixel, we will look around it and we make some sort of average. Well, the problem is that when we do that, we have all these oscillations that appear along transversal lines. And instead, if we compute directly on the level lines, we would have a smooth variation of curvatures according to how much we bend the line itself. And the algorithm that we have implemented, and as I mentioned, can be tested, starts with an image, extracts the level lines. Now, the quantization step for the level lines extraction is a free parameter. And then, since the level lines are polygons, closed polygons, we can compute the discrete curvature. But if we try to compute it, as mentioned before, directly on the extracted level lines without any smoothing, we will still have these oscillations. So, by short time smoothing, we won't deviate much from the original shape, but we will have a nice variation of the curvature. So please remark here, well, I'm sorry for the shade. So here would be the positive curvatures. Here the curvatures are 0, and at this point, let's say here, the curvatures are negative. Now the thing is that when we try to do this, we work with pixels. Level lines are given at subpixel accuracy. So therefore, inside a pixel, or more precisely a dual pixel, we would have several level lines passing by, and therefore several curvatures. So in order to display this type of to have such type of display, one could have several options: either do an average of the curvatures or choose a median value. So our option was to choose the median of all the discrete curvatures passing through the pixel. Okay. At the same time, whenever we have these curvatures, there is also the possibility of computing what we call topological curvatures. Here, for example, is an undiscriminable texton. I don't know if you see it well, but we have 10s in the middle and s's close to the borders. So human eye could not distinguish that we have actually two shapes here, because we have the same orientation and the same, basically the same curvatures. When we try to compute the curvatures by the scalar or by the one-day differential operator, we get this figure in the middle. So you will have alternations of green and red. Whereas if you compute the topological curvature, meaning that the positivity is given by the convexity or the concavity of the curve, you would have, I don't know if you see it well, so in the middle you will have the 10s, for which we have only green and yellow displayed. Okay, so when you try this algorithm online, we're actually left for free 3 parameters, and one would be the scaling factor. So you just move out and you zoom on a region that you would like to see details. Then would be the quantification step for the level lines, meaning that the larger the quantification, the higher the quantification, the fewer level line you will see. So you will start with a level line with, let's say, level 0.5, and if the quantification step is 16, then the next one you would see would be 16.5. And another parameter 3 is the normalizing scale. This normalizing scale is a smoothing scale such that a circle with a radius, let's say 4, would disappear at scale 4. Okay, so our interest was to leave these parameters free, because one may be interested either in curvature densities to characterize or to classify objects, or can be interested in shape and texture details. Okay, and I would like to mention in the end three applications of this tool. One would be for bacteria morphologies. So, well, bacteria are characterized by the cytoskeleton and by the bacterial wall. Well, high oscillations of the curvature will give us information with respect to the bacterial porosities, whereas smooth oscillations on the border will let us know that here we would have a bacterial wall. Another application would serve for digital elevation maps, in which case the gray level will represent the elevation, the true elevation of the ground. So the lightest the level, the highest the elevation is. Now in this case, level lines are true level lines of the ground, and computations of curvatures will give us information according to whether you go uphill or downhill on the region. And the last application is that I'm presenting concerns the fingerprints. Now, fingerprints are characterized by the cores, by the bifurcations. I don't know. Let's see, bifurcations here, and by the ridge endings. So we need a careful smoothing so that the endings won't mix up together when we diffuse, and also the computation of curvatures at subpixel accuracy would give us the terminations or the ridge endings. And this basically is the information that one needs to know in order to classify and distinguish fingerprints. Okay, well, to conclude, I would like to point out that on one hand, we constructed an image smoothing algorithm that gives a connection, explicit connection between the curve shortening problem and the level and the analytical problem. Then we introduced an algorithm that is serving for denoising, especially as a grain filter, as the mean curvature motion is known to be a good grain filter. So this is just to remove impulsive noise, for example. And let's say the main outcome is the visualization of the level lines at arbitrary resolution, as well as a precise and accurate estimation of the curvatures. And I will end up just by pointing out some projects in some works in projects. So one would be the simultaneous erosion and dilation. Now this is an open problem actually. It has been for like 30 years in mathematical morphology. And why that? Because people, in order to erode and dilate a figure, they use tiny little dilations and then alternate with tiny little erosions. So they alternate and then they show they converge to the simultaneous one. Now, whereas this equation that I've written over here performs both at the same time. So basically you would move, if we have to reformulate this problem in terms of an analytical PDE, you would have a backward and forward aconal equation, where the backward and forward is given by the sign of the curvature. And so with Jean-Michel and another student of his, Rachel Safar, we are trying to use the same scheme, stack filter on level lines, to show the equivalence. And with Antonin Chambol and Gilles Touroud, we are trying to give a variational formulation for this problem. And well, at the same time, I just saw that in the afternoon there would be a talk on integral differential equations, so I'm also interested in that and working on, well, a more theoretical point of view, like large time behavior, regularity of solutions. So here you would have non-local terms like the fractional Laplacian with drifts and so on. Okay. So the algorithm itself is explained in the first paper, which appeared recently in SIAM multiscale modeling, and the equivalence proof has been submitted a couple of months ago. And at the same time, you can find the online algorithms, one on the image curvature microscope, and we have also implemented the finite difference schemes for these two evolution equations. Okay, thank you for your attention. I don't know how am I doing with time? It's okay. Okay, perfect. Okay, thank you. Yes.
So for the level line evolution, you are not evolving to time equals infinity. You stop after a few steps. Yeah.
Yes. Yes. Yes.
Because if you carry on, eventually the lines will be.
If I carry on?
Straight line or something.
Yes, actually, when you perform, Grayson has shown a result stating that if you have a curve and you perform curve shortening, then this curve eventually becomes convex, and in the end it goes to a circle and it will disappear. In the discrete case, we use the discrete formulation for the intrinsic heat equation, meaning that we take the polygon, we do a discrete convolution, and then we parameterize by its natural parametrization. But we have to do this for short times. Otherwise, there will be self-intersections, violation of the comparison principle, etc.
So when do you stop? Like 5 steps?
Typically, typically it depends on the, let's say, the variation of the image. So it would be for, well, the level lines are also registered with a certain accuracy, meaning that per pixel I'm considering a level line to have 5 control points on the level line. So if I take this, then I would have to go with a convolution kernel of standard deviation 3, let's say. I will go with, let's say, between 10 and 15 iterations. This is because you have to take short time smoothing, so.
So when you do the shortening for each level line, so the polygon is not a polygon anymore, is it?
A polygon. Yes, it will. In the discrete case, it will remain a polygon.
So you just move those vertices,
Yes, I move those vertices.
and then you reinterpolate the value to the grid line after motion.
No, I don't need to reinterpolate you mean to plot the level lines or to reconstruct the
Not
image?
plot, but you return it to an image. You need
Oh,
to define.
actually, it's not necessary to reinterpolate and to compute the image itself. We could do that. But it is enough to know where this level line would be intersecting the grid to be able to reconstruct the image. So if you consider all of the intersections with a horizontal line, you know whether the pixel is inside or outside the level line because you have the equivalent principle.
Then the value, how you determine the value, you have to do it in some.
Oh, the value is determined by the fact, since you have a tree, you can start with the greatest level line and then go into its descendant. So you will update the value with every new level line that you have as you go into it. Yes?
I have a question. So it's very nice, but what happens? Suppose so these level lines correspond to an image, right? So you should have two images corresponding to these things. So on the image on the left, the original image, what happens if you just smooth it and find the level lines? How do they look?
Oh, you will still have, unfortunately, if you have the image and you try to get the level lines, you will still have these tiny oscillations because the image is digital.
Yeah. The question is, you have two corresponding images, correct?
Mm-hmm.
So one is like this one,
Yeah.
corresponding to the left one. You want to go to.
This is.
Oh, wonderful! Can I have the next one?
Yeah.
Oh, fantastic!
Okay.
So go back to this.
Okay.
So here. So what happens if you just smooth this image?
Yes.
Find out
Which are the level lines?
Find out the level lines.
Mhm.
How do they look?
They would look a little bit smoother than these ones, but you
Uh-huh.
would still have the tiny oscillations. Because, well, here what I didn't say is that I said actually that we are using bilinear interpolation. And since you're using bilinear interpolation, you have an explicit formula for the level lines. You know that level lines are pieces of hyperbola or straight segments. And then you have to concatenate. So at the points where you can concatenate, you will have just, imagine a transversal line, you would have something like this doing. But that would be smoother, of course, than this one.
Yeah, I mean the whole point is get a smoother image, right?
Mm-hmm. I can show you, I have
Oh,
performed this, so I can show you on my computer,
Yeah, sure,
yes,
sure.
the result. Mm-hmm.
But I think that if you, depending on the size of the kernel, if you smooth, you can also lose the topology.
Yes,
Of the-
exactly.
of the
So you have to
levels.
take a kernel with a small compact support, with a small support.
But if you know the noise, then you probably can probably observe that.
If you know the noise.
I mean the distortion or whatever.
Oh, yeah, probably you can do it alternatively.
Thank you very much.
Thank you.